I'm Kerry Fowler. I work for a biotech in town called Kineta. I'm a chemistry department of one. It's not the first time I've done that, so if you have any questions about careers where you're the entire department, please see me afterwards. I'm a member of the Puget Sound section of the ACS, and I want to thank Scott for inviting me, along with several other members of the section, to introduce the speakers at this meeting. Am I making changes to the slides? Okay. I have to admire Scott for, he seems so chill about this whole thing. I would be a total wreck if this were my meeting, and he seems to be handling it with great aplomb. And it's the cocaine. I think that's the wrong drug in this case. We actually have a legal drug that would be a little bit more appropriate. Also, I have to say, Scott, you also would fit in totally. You just have the look for Seattle. So if you ever wanted to move here, you would fit in perfectly. I also want to thank Paul Hopkins and the University of Washington for making this all happen. So a little preface here. When Professor Nakamura was a postdoc in Gilbert Stork's lab at Columbia, I was up Interstate 95 in Cambridge at MIT in the Buchey group. And so it was a great place to be because I got to see seminars at MIT with all these amazing people, but I could also drop in at Harvard and see talks. And whenever I would go, this is my memory, there would be someone introducing the speaker, and the introduction would just go on, and it was very elaborate and drawn out and lengthy. And then the speaker would come up, and it appeared to be the tradition that the speaker would then say, "In the short time remaining, I would like to tell you about my work." I will try to keep this introduction succinct so that you can hear from Professor Nakamura in the short time remaining. Professor Nakamura is a native of Tokyo, and he received his bachelor's at the Tokyo Institute of Technology under Professor Mukayama in 1973. And then he got his PhD with Professor Kuwajima at Tokyo Institute of Technology, and then a postdoc, as I mentioned, with Gilbert Stork down the road at Columbia. His academic experience started in 1980. So from 1980 through 1995, he was first assistant professor, then associate professor, and then full professor. And he also served as an adjunct associate professor in the Department of Applied Molecular Science at the Institute for Molecular Science from 89 to 91. And since 95, he has been a professor in the Department of Chemistry at the University of Tokyo. And he also had a stint as chairman during that time. From 2004 to 2010, there was the Erato-Nakamura Functional Carbon Cluster Program, of which he was the research director at the Japan Science and Technology Agency, or JST. And since 2007, he's been the program leader for Chemistry Innovation Global COE program. Now, he's served in the professional capacities as program officer or member of the Japan Society for the Promotion of Science, Science Council of Japan, and most recently, he held a 2012 visiting professorship for senior international scientists with ICCAS in China. Just sounds fascinating. And he has many awards to his name, and these are only the ones in the 21st century. So I will just mention these: the Nagoya Silver Medal for Organic Chemistry, Chemical Society of Japan Award, the Humboldt Research Award, the Arthur C. Cope Scholar Award from ACS, and very notably, the Medal with Purple Ribbon presented by His Majesty of Japan in 2009, which is given to people who have contributed to academic fields, arts, and technological development. So that's very significant. He's also an elected fellow of the American Association for the Advancement of Science, a foreign fellow of the Royal Society of Chemistry, a foreign member of the American Academy of Arts and Sciences, and an honorary member of the Israel Chemical Society. So I'm almost done. Of his many editorial services, he's currently associate editor of Journal of the American Chemical Society and on the editorial board of Chemistry and Asian Journal. So this is only a small fraction of all the stuff that I could have read. So what I encourage you to do is go to his group's website, where you'll find his full CV, and you'll also find a fascinating movie that's called Sonata for Carbon Cluster. So if you do a web search on Sonata for Carbon Cluster, it's a wonderful movie. It talks about Professor Nakamura, his research, has great graphics, and shows him playing music with his wife and some other things. There's also, Carmen Drawl from ACS is tweeting the links to that and to the thing I'm going to tell you about now. There's a 60th birthday remembrance for Professor Nakamura that was written by Roald Hoffman. And I really think you should look at that, because it's just really great. So check Carmen's tweet or do a web search for that. So finally, I'm honored to introduce Professor Eiichi Nakamura of the University of Tokyo.
Thank you very much, Professor Dr. Fowler, for your very, very kind introduction. It's my great honor to be here and in this National Organic Chemistry Symposium for the first time. And I thank, of course, Scott for your very kind invitation and for wonderful banquet. And I have to say that welcome back from the banquet, right? I think my duty is to keep you awake. After nice wine and the red wine, white wine, so that but I think I promise you that this is not boring. This is almost like a movie show. I'm going to show you molecular movies. The problem is that it's a silent movie. It doesn't tell you any music because it's a molecular motion. But anyway, I hope that you learn about something about organic chemistry from different perspective. So here it is. You know that March 11th, 2011, we had suffered from the Great East Japan earthquake and also the largest tsunami since 1869. Okay, the 869. So this is over 1,000 years ago, the biggest one since over 1,000 years. And of course, this is not the issue for engineering. Engineers only care for next year or 10 years, but I think this is the subject of either science or history. The scientists should care about something which may have happened or may happen in the future, perhaps not next year, but maybe 10 years, 100 years, or even 1,000 years, because the principles that we're going to discover should remain the same in the coming, let's say, 1,000 years. So this is really more of the scientific issue. So that at least in Japan, scientists start to wonder about this question. How shall scientists contribute to the society? Of course, it's not just in the past 2 years, 3 years, but we start to realize this one again and again. And then I think everybody would agree that the role of the scientist is to provide solutions to societal problems, which serve the society, and also, of course, in a different sense, we serve for the society by providing dreams for people, including us, including to younger generations. So I'm going to touch on a little bit on the societal issue first. So here's our own approach to energy issue, that is organic solar cells. So this is the prototype, very early prototype of our printable organic solar cells that we started to develop in year 2004, and then we did technology transfer to Mitsubishi Chemical, which is the third largest chemical company in the world. And then this is a sample OPV, or organic photovoltaic device made by Mitsubishi Chemical some years ago. We published a paper 2009, but in this context, actually, paper is not too important. The most important one is how to commercialize it, put this into market. And in fact, Mitsubishi Chemical, after technology transfer from a laboratory, recorded the world record for the organic photovoltaics. That is the efficiency of over 10% they achieved 2 years ago already. Now this year, they have achieved 11%. So this was highlighted in Science magazine. So we're very happy that Mitsubishi Chemical is going to put this into market in a year and a half from today. And this is based on our basic science, of course, because we have been working on fullerene functionalization since 1992, just after the fullerene has become available in milligram quantity. So we had added organic functional group once, twice, 3 times, up to 13 times, and we used this, I would say, N-type semiconductors, electron acceptor, as a prototype for the development of organic solar cells, printable organic solar cells. And with the capacity of controlling the self-assembly, this is one example we published almost 10 years ago, that if you have a long chain on the C60, and then you start to stack each other, and then it gives you an interesting structure in the crystalline state and also in liquid crystalline state. And this is another example, that if you somehow you have this is 5 Fe groups surrounding the cyclopentadiene anion, then if you dissolve this into water, then we discovered that we can have a bi-layer vesicle inside this water, also outside this water, that we published 2000. So we have all this capacity, we use this capacity to make a self-assembly or order the structure in our printable solar cell. So here's I touch on the issues on the decreasing supply of chemical elements. So those of you that who live in the United States may not feel this issue, decreasing supply of chemical elements. But we live in a small country, and then we actually don't have too much supply of anything, including oil and also chemical elements. So we import everything. So that I say, no palladium, please, in our lab. I keep saying this in the past 20 years, because if you work on palladium, you can have a brilliant results like the Jinquan Yu, like today, or yesterday presentation. But I said to ourselves that we don't use palladium. We're going to go for iron. So this is I think the GOC cover page some time ago. This is on, some of the Chinese people may read this iron. And iron is, of course, ubiquitous. There's a reason for that. And also it's non-toxic. So that, of course, it's cheap. So that it's really the way to go. So that we have been trying to get rid of palladium, and this is our version, iron version of Jinquan Yu chemistry. So we could do the same thing that we learned about yesterday, same CH bond activation using iron catalyst, and we got 85% yield, 1.2 grams, 1.4 grams. It's not as good as his one yet, but I'm sure that we can improve it on it because we have been working on this already in the past 15 years. So, but I wanted to have this message to be delivered to the world so that I had a chance to write a commentary in Nature Materials published in March issue of 2011 on the managing of the scarcity of chemical elements. So the issues associated with supply of rare earth metals are a vivid reminder of all that all the resources are limited on the earth. So this is my message. And I'm very proud of the fact that I coined the word element strategy initiative. Maybe some of the Japanese or Chinese people may read this, Genso Senryaku. And I proposed it to the government in 2004. And in fact, 2007, the government started to have the element strategy initiative as a funding, two of the funding agencies started this. So in the end of this commentary, I stated the following. I read it for you. While the depletion of rare elements could trigger a new conflict, it would also serve as an opportunity to make a dream come true, to create new science and technology. It is hoped that as many researchers young researchers as possible will be involved in creating a new world of element science, and will share our dream of opening the door to the future of mankind. So this is what I said. And this is the message, first message maybe for the younger generation here in the audience. So here's the health issue. I just included this because we learned about the PET imaging, positron emission image, tomography imaging presented by Professor Fowler this morning. So in fact, we did something on this direction. And as she mentioned, part of a slide, that the oxygen-15 has a lifetime of only 2 minutes. So that I thought that it's really a big challenge for synthetic chemists to make use of oxygen-15 to make oxygen-15 labeled glucose. And this is so far the most complex oxygen-15 containing molecule. The next, the molecule with low-level complexity, that's butanol, and then water, and then molecular oxygen. So that by far, this is the most complex molecule, and we had been able to have some success for the imaging of small animals. And so I finished discussing briefly this, that we should contribute to the society. But of course, then next main topic today is to provide dreams for people, including, let's say, school children. By the way, this is a picture of Mount Fuji, which is now registered as World Heritage. And this is a picture I took myself on the plane going to Beijing last year. So here we have a Pacific Ocean. This is actually Pacific Ocean. And we have Izu Peninsula, and we have we see 1, 2, 3, maybe 4, and actually there are 5 lakes surrounding this. Please come to Japan and go up here. This is like Mount Rainier. This is a very amazing mountain that you can see the bottom to the top from the sea level. So you can see this 3,777 meter, the whole thing from the bottom, the foot, and to the top. So here I say a smart, small molecule and real-time imaging for organic molecules. This is the main subject of the discussion today. So I'm going to talk about the imaging of conformational change of a single organic molecule. I'm going to talk about chemical reactions of maybe 2 molecules or maybe single molecule, bimolecular or unimolecular reaction. And in the end, I'd like to spend some time on the mechanism of heterogeneous nucleation organic crystals, generously supported by JSPS and JST, essentially Japanese government. So this is the first picture of the first motion picture of the conformational change of small organic molecules. So this is the first time reported in 2007. So this is a very lousy digital camera. So because it's very slow exposure time, 0.5 second exposure time, and there's a data retrieval time of 1.6 seconds. So that this picture, each time we took 2.1 second interval. But anyway, this is the real-time picture, and there's no computer processing. Okay, this is what we took. And as you can see, to see 2 lines, and these 2 lines are the carbon nanotube. So carbon nanotube is like this. We learned about this from the Larry Scott lecture. It's like tube, and then of course on the top and in the bottom you have a higher density of carbon. So that is shown as 2 lines. And here we see a head. This is a carborane, B10C2. And this is a C22 side chain. And the length, as you can measure, is 3 nanometer. And by now, perhaps you have seen that it has 2 chains. It looks like one, but once in a while you see 2 chains, because this is like a wobbling back and forth. It's a repeating movie, so it starts again. Yeah, here it is. Yeah, you see clearly 2 chains. One chain again, dark, and you see 2 chains. Dark because we have overlapped, two chains overlapped. Less dark because you see two chains independently. So here are 4 compounds, or maybe molecules that we synthesized. And here's the question. Guess what it was? I think it's obvious. Because this is long, this got to be 3 nanometer, which is a 30 angstrom long, and this has 2 chains. Because other things, this has a short chain, this is C12, too short, only 1 chain, so that these are not the molecule that we have just seen. But this means that this is an ultimate microanalysis, right? Because you have seen only 1 molecule, and we have determined the structures. The resolution is not that high, so that you cannot really tell what it is. But if you are given these conditions, then we can immediately tell that it is it. And because it is ultimate, because without any molecule, you cannot do any analysis, of course. You need at least 1 molecule, and with this 1 molecule, we have determined the structure. So I claim that this is the ultimate microanalysis for organic chemistry. So here's the configuration, because many of you have never touched on the electron microscope. So that I just show you a brief configuration. I explain to you how it works. So here is a picture of optical microscope. Here's a naked eye. And here's a sample, and you have series of lenses, and here's a lamp. So the electron microscope is the same, except that you use electron source and then use a magnetic lens rather than the glass lens or plastic lens. Because, of course, if you have, and also everything is in vacuum. Because the electron interacts strongly with glass, we cannot use glass, but the electron is charged minus, therefore you can use magnetic lens. So, but the overall configuration is the same. So you have an electron gun here, and the sample here, and the series of lenses here and there, and you have CCD or this CMOS camera. And it looks like this. This was the motion picture I've shown you was recorded on an ordinary TM, which is made by Gero company, 2100F. It has a 2.3 angstrom spatial resolutions. It's just a bit short to get 1.5 angstrom, right, which is a CC bond. But people have the capacity to make an instrument up to 1 angstrom resolution. This was the best machine in 2004, but it is actually common. You can see almost every institution in the world. This is now it's a commonly available machine. That means that you can record the movie that they have just seen by using any of the best TM you have in your school or institution. So the technique is now available for everybody. So this is a little bit more sophisticated. This is a helium temperature stage, which is actually, there's a helium cooling apparatus here, and it is aberration corrector, and the resolution is less than 1.4 angstrom, less than 0.14 nanometer. The best conditions, it has almost one angstrom resolution. So this is how we connect the real world to this molecular world. So in this particular situation, here's a sample holder. There's push sample in from here, and samples are held on the real world grid. Okay, this is 1 millimeter, and you see the hole here and the hole here, and you see lacy, what they call lacy carbon. It's a carbon, but it has a hole in it, the 10 micrometer, and this is 1 micrometer. Each time is 10 times larger. So you have this part here, and you see something sticking to this, and then this 100 nanometer, then you see the round object, and then the 10 nanometer, you see something here. Looks like a horn. This was discovered by Professor Iijima. This is one variant of single-wall carbon nanotube, but it looks like a cow horn. Therefore, he named it as a nanohorn. So this is nanohorn. This is 1 nanometer. We have come from 1 millimeter to the 1 nanometer. So here's carbon nanohorn, and this is vacuum, okay? Remember that the TM operates on vacuum, in vacuum. So here we have something sticking out, and this is it. This entity you see is actually bromine atom. 1 bromine, 2 bromine, second bromine. And here I think it's more or less like a phenyl ring. I'll show you this motion picture later. But anyhow, this will carbon nanotube. We have a molecule, bromine, 2 bromines, and 1 phenyl group seen. Not at high resolution, but you can see it. And you see the motion picture later. So from real world, we come down to the molecular world. And this is subject today. So you can also do elemental analysis. That's really the charm of electron microscopy. SEM, TM, you can do elemental analysis. So here's the excitation of the electron in the K shell for the carbon and also boron. So clearly, you can differentiate the elemental composition. So this is the EU's electron energy spectrum of the compound we have seen. We have a boron, we have a carbon. So therefore, it's a summary of the methodology itself. It is an ultimate microanalysis requiring only 1 molecule for studies of structures and reaction pathways. And I would say that it will tell us 6D information, 3D structure of a single molecule, 4D time evolution of its motion reactions, 5D, 4D information, many molecules, and perhaps we can say 6D because we can study elemental composition at nanometer scale. The reason why I said 3D is the following. So this is like an ordinary, not the most modern 3D, but the ordinary motion picture, TV. So that TV shows, in fact, shows you 3D information because I just turn around like this, right? So there's more information than just camera. Yeah, so that I argue that it's actually 3D information. I've published our work in Science magazine 2007, but it almost failed to be accepted. This paper was almost rejected because of the 2 different opinions. This is a good one. The ability to image conformations of individual small molecules is a holy grail of microscopy, and the authors present a convincing case that they have managed to do so. So this is very good. And this is a very nice comment to the CNE news by Professor Lord Hoffman, who is my good friend. This is the most direct visualization of the motion of the molecule that he has seen. Hoffman tells the CNE news, and it's damn clever. Thank you very much. This was good news, but bad news was that 2 referees really insisted that this should be rejected. Because one says it is not clear what new horizons such imaging technique will allow us to explore. And this person also said that molecular motion is common sense, right? What's nice, what's good for just taking a movie of the molecular motion? The second referee says the TM data are heroic and very new. That's wonderful. However, the interpretation of those incredible images is not convincing at best and dead wrong at worst. I'm going to convince you that our interpretation is so far so good, okay? What you see is what you get. And even 2010, this was the JAX referee. The electron dose is much higher than the accepted electron dose, which completely destroys molecules. So this referee said it must be computer processed. He did not believe the pictures. And it was flatly rejected by German office in Germany. And after 3 years, we are now preparing a rebuttal so that we push this paper back into JAX as an article. So it takes a long, long time to combat with the referees. I know that as an editor of the journal. You should be very persistent. Because those comments are based on misconceptions among professionals, because I'm really amateur in this field. Professional misconception in the TEM community about the cross sections of collision and ionization with light atoms. The thing is that cross-sectional collision with single carbon is very small. It's known to be true from the J.J. Thomson's lifetime, time that's in the 19th century, where somehow TM specialists have never thought about the very basic chemical physics principle. And misconception in the chemical physics community that molecular motions are always very fast. It's very fast in the gas phase, but remember, our case is very special. It's molecules are loosely connected to the carbon nanotube, or inside or outside. So here I classify the situation for the analysis. Okay, one is analysis of molecular properties. One is, of course, in the gas phase. Another one is on the macroscopic surface. This is like STM or AFM. And this is in macrosolid, which is maybe in crystalline state, crystallographic analysis. Here, there's no motion you can see. Here, again, not much motion you can see. And this is only the case that you can study the real-time motion on the single molecule. That is our case. So we have a macroscopic TM column, we have macroscopic sample stage, and we have a mesoscopic, the basic carbon that we have seen, micrometer scale. We have a nanometer scale carbon nanotube on which molecule may be connected by a single bond. So I think it's we can call this a coupled oscillator, coupling small molecule gradually to big object. Small molecule immediately to big object, totally inside, the situation is totally different. So that I think this molecule is picking up the phonon vibration of this entity through this one bond filter. So this is my interpretation. This is my answer to this nasty science referee, the first one, or second one maybe. So you might wonder why I'm synthetic chemist, okay, synthetic organic chemist, still totally synthetic organic. But you might wonder why I started this business. Yeah, here it is. And this is the motion picture of for the addition of lithium dimethyl cuprate dimer onto methyl vinyl ketone. We published this in JACS 1997. And we published also extensive review in chemical reviews last year. This is very good for graduates, organometallic graduate textbook in a sense. So we have seen this, been seeing such a thing on computer, and about, say, 10, 15 years ago, I thought I wished to see the real one, real molecule, rather than the virtual molecule. So that was my dream, almost for 20 years. Then I have an opportunity to address this issue because the Erato project comes with a huge money to one person, which was me. Only four people selected every year out of all field of science and technology in Japan. So that I proposed that based on organic synthesis, I made various derivatives of C60 carbon nanotube. And I'd like to address the problem of solar cells that I mentioned to you already. We have solved the problem, and now we did technology transfer to Mitsubishi Chemical. And also, we have been doing the DNA and RNA delivery, which I'm not going to talk about today. And also, I proposed the nanostructure analysis that I wish to see the molecules, single molecule. So, and it took us, actually, there was no results for 2 years, year and a half, 2 years, on both solar cell research and TM research because I was amateur. I just started together with the professionals. So that no results, and that's a really sad situation, right? You have got a huge amount of money, no results, 2 years. But we did it, as you see. So this is the first team. So we have hired Dr. Suenaga, who is a top-notch electron microscopist, hired also a young TM specialist from Kyoto University. So we have a TM group, and we have Swedish postdoc, Dr. Sorin, who is now back in Sweden, and also now Dr. Tanaka, who is the graduate student, Dr. Isobe, who is an associate professor in the group. He's now full professor in Tokyo University. So 3 synthetic chemists, 2 electron microscopists. And then we recorded the picture you have seen, which is supported afterward by a series of people. And this person is not related to our project. Dr. Ryoji Noyori, recipient of Roger Adams saw some time ago, but he looks very happy on the side of my former graduate students. Eiichi Nakamura, he's not my relative, she's not my relative. She's doing postdoc in Kish's lab in Harvard now. So we have a technician, Mrs. Nimi, Dr. Harano, who is a staff member, former member Yoshikai, who is now in Singapore, Nanyang University of Science and Technology. And together with the two graduate students, and then in the end, we collaborated with polymer scientist, Professor Ludwig Leibler. So here the same thing, so I skip this. And this is an additional picture that we reported Nature Nanotech 2008. So here we have a carbon nanotube, 3 molecules, and you see perhaps there's a defect, it's a hole. This is a molecule, C60 having long chain, and this long chain is coming out. Initially, it looks like a question mark conformation, right? Question mark type conformation. But it rotates, and it's almost coming out, but since C60 is too big, so it never comes out. And this is less interesting picture. This is something you see every day, right? So it's gone. So this is a more interesting. Focus on this here. Yeah, it comes out like this. Maybe you can show you again. Here it is. So this was taken at 4 Kelvin stage. This was taken at 4 Kelvin. Other pictures all taken at room temperature. So this is very interesting. Room temperature 4 Kelvin, qualitatively, the speed of motion, conformation change was the same, right? So this is one major issue that we are still pondering on. So now, somehow, now the side chain is out of carbon nanotubes. So it's a vacuum. So you see the constant conformational change of this, I think, C10 chain. So this is for the first time we see for human to see the conformation change in vacuum. Previously, this was inside carbon nanotube, so you might feel that something wrong with it. But now it's totally out in the vacuum, and this side chain enjoys CH-pi interaction. But of course, all these are not so interesting. We want to see amide, pyrene, and here it is. We have C60 pyrene from the side. We see the carbonyl group. This is simulation. This is a real one. You see this here. This is a carbonyl CO group coming toward us. And here we see pyrene gradually rotating. And you see here, like a racket. This is the top view of pyrene. This is side view of pyrene. And resolution is such that it does not give us exact structure, but we can guess with some information, we can understand it's a pyrene. So how about the more complex molecules? So we challenge this biotin structure. This is 2.8 nanometer, about 28 angstrom. We put this on the carbon nanohorn and aminate aminocarbon nanohorn. So this we have determined the approximate composition. Carbon 70 million, nitrogen 200,000, and then biotin 20,000. And you have only very small amount of biotin, no X-ray because there's no periodic structure, no NMR, no IR. The only method you can determine the structure is the TM, high resolution TM. So here, I think about 10 conformers. So we have a carbon nanotube, and then see this, one conformation, bent conformation. We have several of those. It's again bent conformation, and we can see we can have a movie. This is the point of attachment because it doesn't move, whereas other parts moves around. So here's the point of attachment. What you see here as a dense spot is the end of biotin. Series of spots you see, and these are the overlapping carbon atoms. the resolution is such that you cannot see individual carbon atom. So here's a large ring. It's like hydrogen bonding here. But you see a big change of conformation here. Smaller ring. We don't know exactly why, but there's a hydrogen bonding exchange. So you see the stem here, which corresponds to the stem here. This is 1 nanometer. So the way we determine the structure is very primitive. So we have many atoms, very dense, less atom, somewhat dense. And if we have CC bond perpendicular to the electron beam, you don't see anything. So that this is interesting because this is quite orthogonal to any method for the conformation analysis. Because you have seen individual conformers already. And you have seen in one case, one conformer went to apparently more stable conformer, and more or less others just stayed in this well, all the local minimum for a long time. So this is a very unique method to sample conformers. NMR, you heat it, and then you see the average. X-ray, you see only one, usually one conformer, it's fixed. But here you can have an opportunity to study one conformer, and you can study the time evolution of conformation change. So this is a summary of what our discovery. Previous microscopic analysis, TM imaging of molecular solid, STM, AFM, all these are, of course, different in their capacity. Diffraction, X-ray diffraction, electron diffraction, you need a molecular ensemble, okay? Many molecules. Here also, UV visible mass spec NMR, you need a huge number of molecules. Elemental analysis can be only done for bulk samples. So our method is totally different from any other analytical method available. So now let's go to the second part, imaging of chemical reactions. The first one is Fullerene dimerization, published 2010. So here's the interesting regio and stereochemical issue. C60 has a pentagon and hexagon. Okay, they dimerize hexagon versus hexagon, or maybe dimerize hexagon and pentagon. So there are two ways. But this issue has never been discussed. Professor Komatsu used to be in Kyoto, discovered that if you treat C60 solid phase with KCN, grind it, he found that he has a D2H dimer. So you have a symmetrical structure, hexagon, hexagon. And they stopped there. We discovered in this study that you can synthesize, in a sense, on the single molecule basis. It's a CS Fullerene dimer. So you see hexagon and pentagon, okay? Hexagon, hexagon, more symmetrical. And also we have discovered that we can study the reaction mechanism. So if two molecules come together that react, then first it collides reversibly, and it may form van der Waals complex, and it may undergo one bond formation, two bond formation, and multiple bond. We have discovered by electron microscopy that dimerization of C60 is reversible up to two bond formation, maybe one bond, and then it's completely irreversible. You can see this picture. So in this is taken 793 Kelvin. That means what? 760 or 780? No, anyhow, 793 Kelvin. And you have a carbon nanotube C60 is dimer. It maybe looks like trimer dimer. Okay. Then we heat it and then took a look at this for a long time. So we have C60, now dimer, they come together. Here it is, here it is. Now it comes here, oops. That was must have been van der Waals complex. And then they have already fused. So that you can study the distance, right? Whether if it is 1.5 angstrom bonding, if it's 3 angstrom, it's van der Waals complex. So this is the picture, motion picture for the dimerization. Yeah, you start to see bond formation. You see dumbbell already. And you see some structure now. This is carbon nanotube, okay? In the end, you see ladder, more like a ladder structure. But of course, this is maybe resolution is too low. Maybe you don't agree with me. Here's a better picture. So this was taken during 1 hour. So we can study each frame carefully. And we have determined the structure of several intermediates. Okay, these are intermediates. One is shown here. It's dimer because these two walls are in bonded lengths. Okay, it's dimer. You see this bridge, you see the hole. And this hole is due to this pentagon overlapping. You see the hole here, and you see the bridge here. So that this we can interpret to be this less symmetrical dimer. So this is dimer, second dimer. Then it undergoes ring expansion because C60 is strained. This is less strained. So you see the crisscross structure. You have a dot, and this can be reproduced only by this structure. So you have this dot, this structure, and you see this, I think it's armchair, carbon nanotube can reproduce this structure. So that we could only, as I said, only a few structures of structure determination. But now it demonstrates we have a capacity to analyze the structure of intermediate by electron microscopy. So now, cis bond reorganization by single ion atom. Come back to ion catalysis. So this is a molecule that we synthesized some time ago. This is what we call buckyferrocene. C60, CP, CP, and 5 methyl groups. And with imagination that maybe we can synthesize C70 by just heating it, because iron is known to be a good catalyst for Fischer-Tropsch reaction or graphene or carbon nanotube synthesis. So it's known that iron is a very good catalyst for cis bond cleavage and cis bond formation. So let's assume that iron just cleaves this bond and do some cis bond formation. And since this is less strained, we hope that this may grow to C70. We did the bulk experiment first. So we have the pentaphenyl compound, and here it is. We heated up the single crystal, and then we observed the formation of biphenyl, phenylated CP, phenylated the ferrocene, and others. And from this, we surmise that this one formed through this single metal catalysis, right? Because this was cleaved, and this was CH bond activation, bond formation. So that I thought that what my dream may come true. So then we examine this reaction by electron microscopy. So here it is, again, carbon nanotube, we see buckyferrocene. We have, this is simulation. Maybe I've explained to you the simulation first. So we have C60, we have CP, iron, methyl. Because what? We have CP, this is simulation, okay? We removed iron, no iron. We remove everything, we see methyl. And therefore, this is methyl, this is CP, and dot here is iron atom. So here it is. This is a real image. We have a C60 trace of methyl group with CP and iron. Without even simulation, you can determine the structure. But this compound molecule turns out to be very unstable because of the catalytic activity of iron. So here it is. I'll show you the motion picture, but it is almost like the C60 dimerization. But so I explained to you. First, these are still pictures. So this is the starting point I've discussed already. This is, let's say, a few seconds afterward. You see that already this wall is gone. You see the iron atom here. You see clearly here the C60 wall on this side is gone. We see iron. Again, there's none of the trace of this wall. We see iron. It looks similar, not exactly the same, but similar to C70. And this wall, if you focus on this wall, it remains intact because this wall is far from iron. So that we have seen the chemical reaction only on the side of iron atom. And all these others, all the same molecule. And these are packed so well that we can surmise that the ingredient of this reaction is only something available in the vicinity. There's no space for methyl groups of CP or iron to come over through this, beyond this molecular plug. So this is a picture, and this is, again, too quick. This is only 15 seconds. If you focus here, actually I have to repeat this, bit nuisance. Focus on here, then it's, this is iron metal. And if you focus here, then this wall is gone, whereas this wall remains intact. Okay, now the third final topic. Where is the new horizon that can only be approached by smart TM technique? And this is very good. Actually, having referee, okay, a referee may be tough on you, but having good referee is very good. Because our science paper referee said, what new horizons? And then this remained in my mind for a long time. So that here's my answer. Maybe one of you may be this vicious referee. Here's my answer. So there's a new horizon that can only be approached by the use of our new technology. We published a paper recently in Nature Materials named Heterogeneous Nucleation of Organic Crystals Mediated by Single Molecule Template. So we have a single molecule template, and we see the molecules gather together to grow into crystals. So how do crystals grow? Why is crystallization so erratic? That everyone knows. Why do we cool down slowly or keep this mixture for a long time at the same temperature? Why do flexible molecules hardly crystallize? Why do we scratch the bottom of the flask for recrystallization? This, I think, is still, we have not solved this, but this is interesting. When you, as a professor, teach students, right, they scratch the bottom of your flask when you want to have a crystals, but nobody knows why. So what is nucleation? We have heard about this, nucleation. Studied for 100 years since Gibbs, the famous Gibbs free energy, and there is a consensus mechanism, okay? It's a physical mechanism. So it is. The crystallization can be separated into two steps, nucleation and crystal growth. Because of this energy diagram, this is controlled by surface energy, R square, which goes like this, and it is working against the chemical potential, R cubed. Chemical potential, let's assume it's a van der Waals interaction. Therefore, it's R cubed. So therefore, it goes slowly, but it goes quickly after a certain size. Okay, this is what they call critical size. So energy goes up and quickly it goes down. And here they call critical size, and this is the crystal growth regime, and this is nucleation regime. And as you can see from the diagram, up to here is reversible. Up to here is reversible. One molecule, two, three molecules, many molecules, and then all of a sudden it goes to the crystals. This is what we experience. But I guess nobody ever seen the process up to here, because it has been known that it is maybe critical size includes maybe 10 to 40, 50 molecules, as determined by molecular ensemble measurement. That is dynamic light scattering or things like this. No molecular picture has been obtained. So no molecular level information available. Now here's a heterogeneous nucleation. I think many people believe that there's really no homogeneous nucleation. It's always maybe heterogeneous nucleation. So some dust, right? So that here's a flat surface, and then one molecule may come, and then somehow it attracts several molecules. It may go to disordered, ordered transition, and it undergoes crystal growth, rapid crystal growth. How does the first molecule become attached to the surface and grow into crystal? This is a very fundamental question. But there have been no methodology available. So we have the methodology. So there have been an argument that heterogeneous nucleation is more, it's not arguments, it's known. Heterogeneous nucleation more facile than homogeneous nucleation. Here's the argument. Heterogeneous mechanism is very difficult to study. Therefore, people thought that heterogeneous mechanisms are different from homogeneous mechanism. So that is, this is the, I think, common statement in the society. The heterogeneous nucleation mechanism is different from homogeneous, and suggested the importance of surface periodicity. The periodicity of a groove or step induces the periodicity of molecular ordering leading to crystals. So this is very simple. So if you scratch the surface of the glass, so you have a step like this. Right? So the molecule, let's say this one, molecule comes in, and then they're aligned. Therefore, the periodicity on this step is reflected on the molecule. So physicists say that this is a mechanism of nucleation. And our study says this is least possible. You need only single molecule for nucleation. Our mechanism is a single molecule that is, of course, non-periodic, induces periodicity of crystals by stochastic process. So this is the experiment we designed. Actually, it's based on serendipitous discovery. So we have carbon nanohome. We have seen this. Amino carbon nanohome, we made amide. We put on this Y prime template having 2 bromine atoms. Here's a Y molecule, symmetrical. And we have this molecule. With this template, we could crystallize, induce crystallization of 2 different molecules. So here is the substrate, carbon nanohorn. Carbon nanohorn is the assembly of single carbon nanotube. Having, in our case, we have amine. So this looks like this, the 50 nanometer scale. Now it's 10 nanometer. And the structure, as I mentioned to you, C70 million to C170 million, and it contains certain number of nitrogen. It is water soluble, and it can manipulate like a polymer. So this is the substrate that we selected because it has we have a crystal structure, and it has only one polymorph, crystal polymorph, and I show you, and also bromine. These bromine atoms are necessary because of the low resolution of our current methodology. So in this crystal is made out of 12 molecules and 3 times 4. The basic skeleton, basic pair is here, shown here. Pi-pi interaction CH pi. So this makes a chunk of 3, and times 4 makes 12, which is unit cell. So you see this, you don't see too much, but you can see this. I show you this same picture, but now I show you the motion picture. Here it is. So you see the motion here, and see once in a while you see bromine atom. You see constantly phenyl group here. And this is somewhat slow because there's a confinement here. You see bromine here. Here it is. You see a phenyl group. Yeah, you see sometimes 2 bromine atoms. Yeah, so that we know that we can even count numbers of templates. So we have this template, we have a molecule 2.78 milligrams, and we recrystallize this in the presence of 10 to the minus 4 equivalent of template. And we have a large crystal. This is optical microscope. 280 micrometer means 0.3 millimeter. You have 10 to the minus third. This is 10 times more, and the crystal becomes smaller because we have more seeds. So it's a summary. There, 0 seed, there's no seed, then this is the average length of crystals. This is almost like 1 millimeter, 10,000 micrometer. And the yield is very small. And you have 10 to the minus 4 equivalent, fourth equivalent. Then you have a much shorter crystals and a much larger yield. So this is the one indication that our template acts as a template. And this our templated carbon nanohome stick to the surface of these crystals. You see the high affinity. But if you have no template, that's amino nanohome itself, this is small crystals and not much crystal growth. And on the crystal, you don't see any of this round object sticking to, because there's no affinity. And here's a summary of our discovery. So we have a template where we recrystallize ethanol solution of this Y molecule. We saw crystals, and we saw molecular clusters, disordered clusters, pre-nucleation cluster. Here it is. We have carbon nanotube. Oh, so by the way, we remove a template because it's a carbon nanotube insoluble. We remove the template, my millipore filter, and put this onto the TM. Okay? So this is not in situ analysis. This is ex situ analysis. We have a vacuum carbon nanotube. We see 3 molecules. And if you focus on this particular point, this point doesn't move, whereas the other moves. Therefore, we conclude that this is the template. So this is one of those frames. And here's a molecular model. It's a simulation. I argue that the simulation is good enough, right? Something over here, something over there. And this template 2 different molecules. So that from here, we conclude that we have seen the pre-nucleation cluster made of 2 + 1, those 3 molecules. Here is the pre-nucleation cluster, sometimes called embryo, composed of Y'1 plus perhaps a dozen molecules, up to 15 maybe. So you have a disordered cluster here and the things that are sticking to the surface. And this has been, people imagined about this, okay? But for the first time, we have identified this boundary film, what people thought about, is boundary film. And most of the molecules actually sticking to the surface. This is like cluster, and we have most of the molecule on sticking the surface of carbon nanotube because carbon nanotube is essentially activated carbon, charcoal. Yeah, so that it just absorbs, there's a physics option. So we can count the numbers of a template, which is 6,000, okay, 6,000. And then all the small clusters, 20, with this 5. This composed of 3 to 5 molecules. This is the largest one we have seen, composed of 12 to 15 molecules, counts only 2. And then we saw many of the large micrometer crystals. We didn't see anything between nanometer and micrometer. That means we didn't see any needle crystals growing from here. We saw only template and small clusters and huge crystals. And we can count numbers. So here we have 1 template. We count 1/300 pre-nucleation cluster, disordered cluster. And then we saw 1/3 billion crystals, very small number. And we interpret this number as the 3 to the power of -15th or 4 to the power of -15th. Why? We can interpret this as follows. 15 molecules, okay, 15 molecules is critical size. 15 molecules with 3 to 4 possible orientations take the best orientation at the same time. Perhaps you imagine that with a unit cell that goes like this, and if all molecules have the same orientation, all of a sudden it gains lattice energy and start to grow. That is our interpretation. It's yet to be proven, but it's our interpretation, working hypothesis. So that means disordered to ordered transition is a stochastic process depending on the cluster size and mobility of the molecule. Therefore, it's erratic, and you need slow cooling and flexible molecules, hard to crystallize. At the same time, like a steroid, 2 rigid molecules is hard to crystallize because they find a difficulty to find out a good orientation. So it's hard for them to reorient themselves. You need heating. And I think this has been experienced by many of the pharmaceutical company people. You have to have a heating for a long time to get the best crystal polymorph. So conclusion is the periodicity in the crystal is gained as the result of random motion in the precursor cluster as controlled by the weak template molecule interactions. And this is different from the conventional view. And also, actually, the referee of our paper said, oh, this actually indicates that homogeneous nucleation and heterogeneous nucleation share the same mechanism. This, again, is finding. Why doesn't activated charcoal promote crystallization? Maybe I skip this because the time limitation. So what's New Horizon? The smart EM imaging offers new opportunities in science, technology, and education. And here's the last message. I think the chemistry provides solutions for the society. So most of us work in the lab on the core science up to maybe 10 angstrom regime. But once in a while, we work on the nano integration regime between nanometer and maybe 100 micrometer. And I think we should always have in mind that we are also shooting for the target in our case, gene delivery or maybe organic photovoltaics. And with this, I'd like to conclude my presentation. Thank you very much for the invitation. Thank you very much for the attention.
Okay, I think we all know the drill. Step up to the microphone. Please say your name and your affiliation. Well, there's nobody in the balcony, so we don't have to worry about them.
So I guarantee that nobody is professional in this field, including myself. You can ask any questions you have.
I have a question. I remember seeing recently that the IBM researchers had made a movie that shows a boy bouncing a ball. So they did this by moving atoms around and just making several frames. Is there an intersection at some point between what you're doing here with single molecules and
Atoms.
the ability to manipulate individual atoms and put them together?
Yeah, I think imaging of individual atoms by electron microscopy or STM was done a long time ago, maybe 20 years ago. Do you know why? Because metal atoms do not decompose. To the contrary, TM specialists thought that the organic molecules decompose too quickly. There are reasons, but so this was a misconception. So that since we know organic molecules very well, so that we can manipulate this easily, but in fact, organic molecules are intrinsically, of course, more labile than single metal atoms. Yeah, metal atoms much easier to manipulate. We all know this.
So those IBM guys are chumps, huh? So, compared to this. Scott.
Well, just stunning images. I have, Seaberth Temple University.
Everybody knows now.
You have these images of the C60 with the iron surrounded by the phenols, and it seems as if it's extracting cyclopentadiene,
Yeah.
right? So do you think that's just C5 attached to the metal? I mean, there's no high, we think of cyclopentadiene, of course, C5, H5, but
Are you referring to the bulk experiment?
yeah.
Bulk experiment is just a simple organic synthesis, so that we characterize this.
Right.
Oh, yeah. So
No, but you had this metal, I thought, where it looked like there was a iron attached to a...
CP still.
Yeah, right.
Yeah, that is... Oops. I can go back. That question is hard to answer because the resolution is not good enough. And I can answer your question in 3 years after I get the new machine, expensive new machine. Yes, question is where is CP? Well, I don't know exactly. Maybe it's still sticking here or maybe not. I assume that Incorporation of CP is here, cyclopentadiene. Incorporation of CP into C60 should be easier than incorporation of methyl groups into C60, because CP is already pi system. So that I would imagine, chemically speaking, that maybe CP is the first one which became incorporated in the structure. And from here on, it's just imagination, but it looks that it is unsymmetrical. It's clearly unsymmetrical. So that it is possible that CP was incorporated here, whereas methyl maybe not efficiently. But because methyl is, we have 5 methyl symmetrical, but CP is only 1, so maybe CP could have been incorporated in this area, but nobody knows. This is something that computational chemists can play some role, but this is big, huge molecule still with this computational power. And iron is the worst metal to work with because of all these spin states. But in principle, you can study this with computational method. So we have to wait for somebody to do this for us. So I think we are coming to really the end of our knowledge of as a scientist. I think this really it's somewhat beyond what our comprehension.
Are there any more questions? I wanted to just share one more thing. I mentioned the movie that you can see if you go to Professor Nakamura's website. And I just wanted to quote something that he says. Both music and chemistry allow you to express your ideas and emotions. In this respect, they are the same. And I know during this talk, just seeing pictures of molecules, it was a dream come true for a chemist. And I think having been to the other talks, just all this amazing chemistry going on, I feel kind of emotional, seeing it. So please look at that movie, and please let's thank Professor Nakamura. Thank you. Great job.